This is Mrs. Ward reading the chemistry book, chapter 11, section 3, moles of compounds. The objectives of this section are to recognize the mole relationship shown by a chemical formula, to calculate the molar mass of a compound, to calculate the number of moles of a compound from a given mass of the compound, and to calculate the mass of a compound from the given number of moles of a compound. To determine the number of atoms or ions in a mass of a compound. Okay, so it looks like a lot more math for us in this section. You have learned that different kinds of representative particles are counted using the mole. But so far you have applied this counting unit only to atoms of elements. Can you make similar conversions for compounds and ions? So we've been doing with atoms. Can we also do it with compounds? Can we also do it with ions? If so, you will need to know the molar mass of the compounds and the ions. Okay, I'm thinking we know that for the atoms because it's in the table. I can't think of the name. But for compounds and ions, we may have to figure that out. Okay. Chemical formulas and the mole. Recall that the chemical formula for a compound indicates the types of atoms and the number of each contained in one unit of the compound. I'm going to read that again. Recall that the chemical formula for a compound indicates the types of atoms and the number of each atom contained in one unit of the compound. For example, Freon has the formula CCl2F2. The subscripts in the formula tell you that 1 mole of CCl2F2 consists of 1 atom of carbon, 2 atoms of chlorine, and 2 atoms of fluorine that have chemically combined. The ratio of carbon to chlorine to fluorine is 1 to 2 to 2. But suppose you had a mole of freon. The representative particles would be molecules of freon. A mole of freon would contain Avogadro's number of freon molecules, which means that instead of 1 carbon atom, you would have a mole of carbon atoms. And instead of 2 chlorine atoms, and 2 fluorine atoms, you would have 2 moles of chlorine atoms and 2 moles of fluorine atoms. The ratio of carbon to chlorine to fluorine in 1 mole of freon would still be 1 to 2 to 2, as it is in 1 molecule of freon. Okay, so 1 molecule has 1 to 2 to 2, but if you have a mole of those molecules, the ratio is still going to be the same, right? Figure 11.6 illustrates this principle for a dozen freon molecules. Here's the picture down here. Check for yourself that a dozen freon molecules contain 1 dozen carbon atoms, 2 dozen chlorine atoms, and 2 dozen fluorine atoms. Okay, so carbon, and I don't know which one is which, but one of these is chlorine and one of these is fluorine, and there's 2 of each. So if we look at a dozen molecules, we get a dozen carbon, 2 dozen chlorine, and 2 dozen fluorine atoms. The chemical formula CCl2F2 not only represents an individual molecule of freon, it also represents a mole of the compound. In some chemical calculations, you may need to convert from moles of a compound to moles of individual atoms in the compound, or from moles of individual atoms in a compound to moles of the compound. So do you understand that? Sometimes when you're calculating, you might have to convert how many moles of this whole compound do you have, and then find out how many moles of a particular atom in the compound do you have, like we just did down here with the carbon and the fluorine and the chlorine. The following conversion factors can be written for use in these calculations for the molecule freon. Okay, so we have 1 mole of carbon atoms to every mole of the compound, okay? 1 mole of atoms to 1 mole of the compound. There are 2 moles, though, of chlorine atoms in every 1 mole of the compound, and there are 2 moles of fluorine atoms in every 1 mole of the Freon compound. To find out how many moles of fluorine atoms are in 5.5 moles of Freon, you would multiply the moles of Freon by the conversion factor that relates to moles of fluorine atoms to moles of Freon compounds. So here it is. This is the one we want to use, right? So if we're going from we want to know how many moles of fluorine, right? So we know that fluorine needs to be on top in our equation because we want to end up with fluorine. We know, and so we're going to put the compound to the left and the compound on the bottom, and they're going to cross each other out, cancel each other out, and that's going to give us, do the math, and that's going to give us our conversion. Therefore, 11.0 moles of fluorine atoms are in 5.50 moles of Freon compound. Okay, a dozen Freon molecules contain 1 dozen carbon atoms, 2 dozen chlorine atoms, and 2 dozen fluorine atoms. How many of each kind of atom are contained in 1 mole of Freon? Okay, 1 mole, 2 moles, 2 moles, right? Okay. Conversion factors, such as the one just used for fluorine, can be written for any element in a compound. The number of moles of the element that goes into the numerator of the conversion factor is the subscript for that element in the chemical formula. Okay, so here's the subscript, right? Right down here. So if it says in the chemical formula, if it says that there are 2 chlorine, then when you write the conversion factor, you have to put 2 chlorine to 1 mole. Okay, if this were a 5, then you'd have to put 5 moles of chlorine to 1 mole of the compound. Okay, there are some exercises for you to try. The molar mass of compounds. The mass of your backpack is the sum of the mass of the pack plus the masses of the books, notebooks, pencils, lunch, and miscellaneous items you put into it. Okay, the sum, the total, add them all together. You could find its mass by determining the mass of each item separately and adding them all together. Okay, so if you took each one of these items that's in your backpack and you found the mass of each of them and you added it together, it would equal the mass if you put the whole thing together and put it on the balance. Similarly, the mass of a mole of a compound equals the sum of the masses of every particle that make up the compound. You know how to use the molar mass of an element as a conversion factor in calculations. You also know that a chemical formula indicates the number of moles of each element in a compound. With this information, you can now determine the molar mass of a compound. Okay, I'm already making predictions about how this is going to work. I'm going to figure out the molar mass of each of the atoms, each of the parts of a chemical compound, and then add them all together. So suppose you want to determine the molar mass of potassium chromate, K2CrO4, using the periodic table. The mass of 1 mole of each element represented in potassium chromate can be determined. Okay, so the mass is then multiplied by the number of moles of that element in the chemical formula. Adding the masses of all of the elements all of the elements present will yield the molar mass of K2KrO4. So I have 2K. So I have to find out what is the molar mass of potassium. The molar mass of potassium is 39.10 grams. And where did I know that information from? The periodic table tells me that, okay? So that's the molar mass of potassium, and I know that I have 2 moles of potassium because there are 2 molecules of potassium, 2 atoms of potassium in this molecule. There is 1 atom of Cr, what is that? I don't know what that is. And its molar mass is 52.00. And there are 4 oxygens And so we multiply by 4, and its molar mass of that atom of oxygen is 16. So when I get all of those multiplied out using my conversions and add them together, we end up with a molar mass for potassium chromate at 194 and 20 hundredths grams. Okay, so you have to use the subscripts and you have to use the periodic table to find out what numbers they are. Okay, the molar mass of a compound demonstrates the law of conservation of mass. Okay, so in other words, the mass is going to stay the same when you combine things. It's not going to change mass. The sum of the masses, the total of the masses of the elements that reacted to form the compound equals the mass of the compound. So when you put the three things together in a chemical compound, the mass stays the same as if you had them separated beforehand. The mass does not change. That's the law of conservation of mass. Figure 11.7 shows 194 grams or 1 mole of, what is that called? Potassium chromate. And masses equal to 1 mole of 2 other substances. So here's potassium chromate, 1 mole. 1 mole of sodium chloride, 1 mole of sucrose. Notice the volumes are different, right? That must mean that I'm thinking that the size of the atoms or the size of the molecules are different for each of these. The physical size, the volume, is different. Each substance contains different numbers and kinds of atoms, so their molar masses are different. The molar mass of each compound is the sum of the masses of all of the elements contained in the compound.